All right, so for the first question, we see the following image, which shows how a solid's volume that maybe not a consistent size can be measured using water displacement. And that's what this question is getting at. And so what we say is that initially we have an object of an unknown metal placed into a graduated cylinder and we get a volume reading. Then once it's placed into the water level rises and we get a separate volume reading. And remember that this is a volume of this graduated cylinder. And our question is, what is the volume of the object? And so to solve this one, we want to first look at the initial volume, and that's 35.14 milliliters. Then we want to look at the final volume, and that's this 64.19 milliliters. Then we want to see, well, what is the change in volume of this graduated cylinder? Because whatever that change in volume is, will be the volume that this object would have occupied. So to calculate this, we want to say, well, the object volume, therefore, must be the change in volume, or delta V, with this capital delta, the triangle, being a symbol for change. And therefore, this is the final volume minus the initial volume. Whenever you see change of something, that's going to be final minus initial for that property. So the final volume minus the initial volume here. Then we just go ahead and use those numbers that we've already determined. These would be things that you would read off of a graduated cylinder in a lab, and therefore the volume of this object is 29.05 milliliters, and that's the answer to part A. Going off of that, we say, well, now we take this object from part A and we put it on a balance, also known as a scale, and this is a pounds measuring scale, and we get a value for that. We want to calculate the density of this object in terms of grams per milliliter. So how do we go about solving this one? Well, the first thing that I would recognize is that we need a formula for density. And while we can memorize formulas, I think what's even easier is we just say, well, the density needs to be in grams per milliliter. So if density is grams divided by milliliter, how do we get that value? Well, we just say it's grams divided by the milliliters. We take the mass and we divide it by the volume. Grams is a unit of mass, milliliters is a unit of volume. So if we take the mass in grams and divide it by the volume in milliliters, that'll give us the number of grams per milliliter of this object, the density of this object. So that's our starting point, and what we now need is we need to get the mass in grams and the volume in milliliters. So the mass we have, it's 0.53 pounds, and note that this isn't exactly the unit that we want right now. The volume we have from the previous part, right? This is the object from part A, and we know based on our calculation that the volume is 29.05 milliliters. Now, if you did calculate a different volume for part A, you're going to get a different answer for part B here, obviously, but I would still consider that you got the answer correct if you followed all of these steps here and that everything is sort of in agreement with this solution, even if the actual number is a bit off. How do we get the mass in grams? This is a classic unit conversion problem. We see within the problem statement that 1 kilogram is equal to 2.205 pounds. This is what we want to use. It'll let us use 4 significant figures. And we also know how kilograms and grams are related. So for this, we want to set up our units, our ratios, and we say, well, it's 0.53 pounds. We start with what we know. It's going to undo pounds, so pounds go in the denominator, kilograms in the numerator, as that is the conversion that we have. Pounds cancels. Now we need to get rid of kilograms, so in the third conversion, or the second conversion we use rather, kilograms goes in the denominator, grams goes in the numerator, and we can convert into grams. 240 grams, 2 significant figures, and that is because we're limited to 2 significant figures based on our 0.53 pounds measurement that we have as given from part B. Therefore, the density here, we have the mass in grams, we have the volume in milliliters, and the density is going to be 8.3 grams per milliliter, again limited to 2 significant figures based on our initial mass measurement. And this is worth pointing out here that even though we want to record the mass in grams as 240, when we do this calculation, it's better to use all of the significant figures that you got from your mass in grams calculation. And the easiest way to do this is just to carry forward on your calculator. So you do 0.53 divided by 2.205 multiplied by 1,000. That value you'll carry in your calculator and it'll have the full screen of significant figures. Then go ahead and divide it by 29.05. We don't want to round before we finish the entire calculation. And this density calculation, even though we've broken it into pieces, can be shown as a single calculation. Part C says that now that we have a density that we've calculated, let's look at this table and predict the most likely identity of the metal. given that we're confined to the metals that are on this table. And so here, this is kind of like an identification type of problem where we've calculated the density and now we want to predict the most likely identity based on only this information that we're given. And so this is a question here is we want to say, well, of these different metals, which has a density that's the closest to the result that we got in part B? And the answer is going to be iron. This is the metal that's closest in density to 8.3 grams per milliliter, and that's the answer to part C and the best that we can do based on what we have here. Okay, so now that we've kind of completed this theoretical experiment, we want to see what we think about what happened, right? Do we consider this a precise experiment? Do we consider it an accurate experiment? And we want to comment on these a little bit. And so as we look through the solution, keep in mind that there's more than one way to interpret this, but I would say that the broad strokes do have to have some common foundations, right? And so I'll discuss my answer here and point out where you may have had different answers or where, they're sort of more open to interpretation. So as we want to evaluate our experiment, we want to say, well, what's the calculated value? And that we calculated here is 8.3 grams per milliliter. That's what we calculated based on our experimental data. What is the proposed real value that we got from the table, the literature value, if you will? And here, as we were confined to the table that we had, we'll say it's 7.87 grams per milliliters, which was that iron value. And so the first thing we want to look at here is, are these in agreement, right? Is this close enough or is this not really close enough, right? And the next thing we want to look at is how precise was our data? How many sig figs did we collect with our data along the way? How well was the instrumentation we used suited to this experiment? And so as you think about this, right, really the first one is the accuracy question. How close is this to the value that we found? And the second question is the precision question. How many sig figs were we able to get, which shows how precise our measurement tools may have been. And so what do we think about this? And I think that the conclusion that you have to make here is that this is neither really accurate nor precise. So first of all, it's inaccurate, right? I don't think that 8.3 versus 7.87 when it comes to density of a metal is good agreement. I think that with the tools that we have, we should really be able to get a better result as far as agreement. I think that we have the capability of being within, only 1 or 2%, rather than this result, which is more like 5%, I would say. And so, if you didn't get an accurate result, it's not very easy to conclude that your precision was very good. And indeed, if we think about the number of sig figs we had in all of our measurements, I think the volume measurement was pretty good. We had 100th of a milliliter precision for the volume. It doesn't really get a ton better than that. But for the mass, I think that only getting 2 sig figs, that really was limiting. I think that something that can only measure to the 100th of a pound, if we're going to do an experiment on this scale, we would need to do better than that and more precise than that, and that could have affected the quality of this experiment. But I think that there is design issues in the experiment as well, and so as you're thinking about ways to improve, some things you might have considered are, you can improve the data collection. The mass only permitted for 2 sig figs. I think that the list that we had here to compare is kind of limited. It sort of assumes that we have a pure metal. It assumes that it's on the list. And so, maybe more research to identify what our calculated value could be could improve the result of this as well. And keep in mind that it could be a blend of metals. So perhaps the target itself isn't really that well suited to this experiment. And it really may not be all that meaningful, if you look at it a bit closer. Now, one thing I definitely want to encourage you is to avoid saying human error. We shouldn't say that this experiment could be improved if we minimize human error. That's definitely not something that we want to say in lab or here, because as we go through an experiment and we complete and collect the data and we report the data, it should be assumed that we used the instrumentation that we selected properly. It's definitely true that, we can misread a value off of a scale or we can misdo a calculation and we're human. However, you should be able to track down those errors and redo the experiment if you need to do that. And so while it may feel like a bit of a catch-all, it's really important when we're evaluating our experiments to say, well, this didn't go well and therefore we should do this in the future. One thing that might happen is say that we're doing an experiment where we care about the temperature of the lab and the temperature increases in the lab. You might say, well, we did this on a hot day and we did collect the temperature in the beginning, but I think the temperature may have increased throughout the experiment, and therefore our measurement of the volume of the gas we collected is actually supposed to be, smaller than it was actually measured based on the temperature we selected at the beginning or something like that. Knowing the direction that it should affect your result, that is a really important part of improving an experiment and analyzing your results. All right, so this was the key to the first quiz. I definitely recommend that you correct your work and try to assess how well you did and use that as a learning experience for what you would want to do to improve your work in this subject moving forward.